Welcome. In this lesson we're going to be looking at the derivative of y equals cos of x and the cos function, where it's more complicated and has dilations and translations applied to it. First we're going to be recapping what cos of x is, then we're going to be graphing cos of x. From the graph we're going to look at what the derivative might be, and then finally we're going to look at the formal laws of derivation for cos of x. So if you'd like to see the formal laws, skip to the end of this video. So a quick recap, what cos of x actually is. Cos of x says that if you have a right angle triangle, which I'll draw to the left here, and it has a set angle x here, there's the right angle, and it has the sides adjacent, opposite, and hypotenuse, then the ratio of the adjacent side, the length of the adjacent side to the length of the hypotenuse side is going to equal cos of x. So cos of x is that ratio. No matter how big this triangle is, as long as it has that set angle x, the ratio is always going to be the same. This is quite a difficult concept, that cos of x equals the ratio. But one thing that's been introduced to the methods curriculum in the teaching side that makes it easier is the unit circle. Because in the unit circle, which I have drawn just to the right there, when you draw a triangle in the unit circle, the hypotenuse will always have a length of the radius of the circle, so that's equal to 1. So cos of x is equal to a on 1. So cos of x isn't just equal to the ratio of adjacent hypotenuse, it's equal to the length of the adjacent side, which I have marked in red in the drawing above. So that length there is the cos of x. Moving over further to the right there, I've got another unit circle drawn there, and I've got the table that many students choose to memorize when they're trying to find those cos of x values. Here is the relationship between this table and the unit circle. Let's pick an angle out of that table, say pi on 3. We go to the unit circle and we draw a line that is pi on 3 radians, which is 60 degrees above the x-axis. So I say here's the angle and here's the line, and it extends up to the circle there. I then make a triangle out of that circle, and the length of the adjacent side of that triangle is equal to cos of x. And just visually you can see it looks as if it's about equal to 1/2, because here's 1 over here and here's a half here. One tip that I have in memorizing these cos of x values is this little rhyme that I say in my head. If I want to know what this cos of x value here is, I mark on the unit circle the values I know. There's pi on 6, pi on 4, pi on 3, pi on 2. And the cos x values, we'll start at 0, go like this. Root 4 on 2, root 3 on 2, root 2 on 2, whoops, that was a bit wonky, root 2 on 2, root 1 on 2, and root 0 on 2. So the cos of x values, they're not the red lines that I'm drawing, but they are the lines along the x-axis that correspond to those triangles. So I'll draw the triangles here. They are these lines which you can see appearing there. So if you do that, there shouldn't be too much confusion or difficulty in memorizing what these cos of x values are. So looking at the table to the right, recognizing that it's got a relationship to the unit circle just to the left, we're going to graph y equals cos x. So starting with 0, x equals 0, on the table to the right, the cos of x value is 1, which is true, because if you draw a line straight along the x-axis, well then the adjacent is that line and it equals 1. So I mark that in green on the axis down to the left. X equals pi on 6, cos x equals root 3 on 2, which is about 0.86. I mark that in again here. X equals pi on 4, cos of x equals 1 root 2. I can mark that in here. I'll just mark in x equals pi on 2, that's 0, and it's halfway between 0 and pi. This will help my graph with some accuracy. And cos pi on 3 is 1/2. There we go. Cos 2 pi on 3 is negative 1/2. cos 3 pi on 4 is negative 1 on root 2. And then cos 5 pi on 6 is negative root 3 on 2. Cos pi is negative 1. So these points, they're not very neat, but you can see the general shape of the cos graph is something like this. And if you keep drawing those triangles in the unit circle, you'll see it actually extends up, around, and then it is symmetrical around pi. Endpoint 2 pi 1. So looking at this graph in red, let's draw what we think the derivative might be. The derivative being the gradient of this graph at different points. So at x equals 0, there is a stationary point, it's a straight line across, the gradient is 0. The gradient then gets slightly negative, we can draw the slope there. So I'll start putting down a slightly negative gradient, and then it seems to increase in negativity until it maxes out at negativity at x equals pi on 2. So I'll draw that max there, and I'll just draw a few points indicating that. It then gets less negative, so the magnitude of the negative gradient decreases, so I can say the gradient's getting a little bit more positive. It's still negative, but it's getting more positive. And then the next stationary point occurs at pi. So we have a 0 gradient there, and then finally the gradient, as you can see, starts to get positive, reaching a max gradient at 3 pi on 2. So I draw those points in, and we can fill in the rest just by following the trend of this. Max gradient, and then down to a 0 gradient across the top. There. This line we've just drawn is the graph negative sine of x. So we can say the formal rule for derivation is, hang on, I'll neat this up, I don't want confusion. If I have the graph y is equal to cos of x, dy dx is equal to negative sine x. That's the basic rule which should influence all our derivations from now on. A more complicated form we could have is y is equal to a cos b x plus c. Or, I'm going to include this one because it pops up, y is equal to a cos bx plus d, and the derivative for both of these is dy dx equals negative a b sine, in this case it's b x plus c, or in that case over there it's negative ab sine bx plus d. So as an example, I'll do it to the lower left over here. We could have y is equal to 2 cos 3x, dy dx is equal to negative 2 times 3 sine 3x equals negative 6 sine 3 of x. Another possible example we could have is y is equal to root 3 cos pi on 24 x plus pi on 12. So b is equal to pi on 24, d is equal to pi on 12, a is equal to root 3. So going by the formula to the right there, dy dx equals negative a, which is root 3, times b, which is pi on 24, times sine, and then what's in there just remains the same. So that's negative root 3 on 24 times pi sine pi on 24 x plus pi on 12.